We now go to the last case, or case 4 of integrals involving rational functions by partial fractions. So for case 4, for each quadratic factor ax squared plus bx plus c that appears k times in the denominator of a proper rational function, there correspond k partial fractions of the form a sub 1 to ax plus b sub 1 all over ax squared plus bx plus c plus a sub 2 times the quantity to ax plus b sub 2 all over ax squared plus bx plus c quantity squared plus, and so on and so forth, plus a sub k times the quantity to ax plus b sub k all over ax squared plus bx plus c quantity raised to k, where a1, a2 up to a sub k, b1, b sub 2 up to b sub k are constants to be determined. So case 4 is similar to case 2, except that the factors considered in case 2 are linear factors. No? So the quadratic factor is ax squared plus bx plus c. Again, it must be essentially quadratic, meaning to say that it is no longer factorable into linear factors. Notice that the contribution in the solution for this quadratic factor that is repeated k times is k partial fractions. No? And for each partial fraction, there are two constants to be determined. So all in all, for the quadratic factor that is repeated k times, there will be two k constants to be determined. And just like in case 2, every time that the factor is repeated, there is an additional partial fraction. And the power of the factor is increased by 1. Alright? So let us have an example. We evaluate the integral of x cubed minus x plus 1 all over x times x squared plus 1 squared quantity dx. So observe that the denominator is already given in the factored form. One linear factor x and a quadratic factor x squared plus 1 that is repeated. So let us work on the integrand by breaking this down into several partial fractions. Okay. So x cubed minus x plus 1 all over x squared plus 1 squared. One partial fraction for the linear factor x plus, we go to the quadratic factor x squared plus 1. So b times the derivative of x squared plus 1 is 2x plus another constant c all over x squared plus 1. So we add up another partial fraction because x squared plus 1 is raised to the power of 2. So d times, again, the derivative of x squared plus 1 is 2x plus another constant e all over x squared plus 1 quantity squared. So x cubed minus x plus 1 equal to, let us combine these 3 and then cancel the denominators. So we'll be getting a x squared plus 1 squared plus b 2x times x, that will be 2x squared times x squared plus 1 plus c times x squared plus 1 plus d times 2x, d2x times x is 2x squared, and then plus e times x. Okay, so let us expand and collect similar terms. So that will be a x to the 4th plus 2x squared plus 1 plus b 2x to the fourth plus 2x squared plus c x cubed plus x plus d 2x squared plus ex. Let us then compare coefficients. So we compare coefficients beginning with x to the fourth. So 0 at the left side. At the right side, we have ax to the fourth and 2bx to the fourth. So plus 2b plus 2b. Then x cubed. At the left side, it is 1. At the right side, we only have c. So immediately, we have the value of c equal to 1. Okay, then go to x squared. 0. We have 2a plus 2b plus 2d. Alright, then for x, it will be negative 1. It will be c plus e. Alright, then for the constant, 1 is equal to a. So we also have the value of a now. Okay, so in the coefficient of x, we have negative 1 plus c plus e. Since we already have the value of c, which is 1, that will be negative 1 equal to 1 plus e. That gives us the value of e equal to negative 2. Alright, so how about b? For b, we have the value of a1 plus 2b, so that means that b is negative 1/2. Then finally, we can solve for d. 0, 2 times a, that will be 2, plus 2b. 2 times negative 1/2 is negative 1, plus 2d. So it gives us the value of d equal to negative 1/2. Okay. So we shall now write our integral as the integral of a 1 over x plus b negative 1/2 2x over x squared plus 1 plus c over c is 1, so 1 over x squared plus 1. D is negative 1/2 2x over x squared plus 1 squared. And then e is negative 2 all over x squared plus 1 squared. Everything dx. Let me move this. Okay, dx. So let us now integrate each term. Dx over x, of course, is ln of the absolute value of x minus 1/2. 2x over x squared plus 1 dx is also ln of x squared plus 1 plus dx over x squared plus 1 is arctangent of x over 1 minus 1/2 2dx, or rather 2x over x squared plus 1 quantity squared dx. So here we're going to apply the power formula. Okay, we have the exact derivative of x squared plus 1, which is 2x. So that will be x squared plus 1 raised to negative 1 over negative 1. And then we go to the last integral. Okay, how do we evaluate the x over x squared plus 1 quantity squared? Well, we have to calculate it separately. So let us delete this part. Anyway, we have already calculated for the values of the constants. So let us evaluate this separately. Dx all over x squared plus 1 squared. So to evaluate this, let us derive a formula so that the next time we encounter such kind of integral, we'll know what will be the result. So let us use u. So du over a squared plus u squared squared. So we derive the formula du all over a squared plus u squared. So here, we are going to apply trigonometric substitution. We use u equal to a tangent of theta. No? The denominator is of the form a squared plus u squared. So let us use u equal to a tangent theta. Du will be a secant squared theta d theta. So du is a secant squared theta d theta all over a squared plus u squared is a squared tangent squared theta quantity squared. So let us write the constant a outside the integral, secant squared theta d theta. In the denominator, we can factor a squared. And then it is further squared. So that is equivalent to a raised to 4. A squared squared is a to the 4th. And after factoring a squared in the denominator, it becomes 1 plus tangent squared, which is secant squared. And secant squared squared is secant to the 4th theta. So a over a to the 4th is 1 over a cubed. And secant squared over secant to the 4th is 1 over secant squared. And 1 over secant squared is cosine squared theta d theta. Okay? So we continue. 1 over a cubed. Cosine squared theta falls under case 2 for powers of sine and cosine. So we apply the identity 1/2. 1 plus cosine of twice the angle, so 2 theta d theta. So 1 over 2a cubed. D theta is theta, and cosine 2 theta, d theta is 1/2 sine of 2 theta. Or 1 over 2a cubed theta plus sine 2 theta is 2 sine theta cosine theta. So 1/2 times 2 sine theta cosine theta is sine theta cosine theta. So we go back to our substitution. Theta, tangent theta is u all over a. So u all over a. So the hypotenuse is u squared plus a squared, or a squared plus u squared. From this triangle, we can now define sine and cosine. So 1 over 2a cubed. Theta, of course, is arctangent of u over a. Sine theta is opposite over hypotenuse. So u all over the square root of u squared plus a squared times cosine a all over the square root of u squared plus, let me rewrite this. Okay, so I shall write this as u all over the square root of u squared plus a squared times a over the square root of u squared plus a squared. There. It's equal to 1 over 2a cubed. Arctangent of u over a plus u times a is au all over the square root of u squared plus a squared times the square root of u squared plus a squared is u squared plus a squared. Okay, so we just derived the integral for du all over a squared plus u squared quantity squared. So going back to dx over x squared plus 1 quantity squared, our a here is 1. Okay, our a is 1 and our u is x. So 1 over 2a cubed is 1 half, no? Because a is 1. Then arctangent of u, which is x, all over 1. So it's just arctangent x plus a u. So 1 times x is x all over u squared plus a squared is x squared plus 1. Okay, so we plug in this value to the integral of 2 all over x squared plus 1 squared dx. So it will be negative 2. So let me write the entire thing down below. So negative 2 times the answer here is 1 half quantity arctangent of x plus x all over x squared plus 1 plus c. Okay, now let us combine the two ln's here. So that will be 1 half ln of x squared all over x squared plus 1. I factored 1 half, so there will be 2 together with ln x, and 2 becomes exponent of x. No? Then plus arctangent of x minus 1 half, negative 1, that will be positive 1 half. So 1 over 2 x squared plus 1. And then negative 2 times 1 half will cancel. That will be negative arctangent of x and minus x. Where am I going to write that? Minus x all over x squared plus 1. Okay, and you see that arctangent x will cancel, right? So we rewrite our answer as 1 half ln of x squared over x squared plus 1 plus, we can combine 1 over 2x squared plus 1 minus x over x squared plus 1 into a single fraction, 2x squared plus 1. So that will be 1 minus 2x plus c. Okay? So let us encircle our final answer. There. So remember that whenever you encounter an integral similar to dx over x squared plus 1 quantity squared, we have the integral of du all over a squared plus u squared quantity squared, which is 1 over 2a cubed times arctangent of u over a plus au all over u squared plus a squared. Another example. We evaluate the integral of x squared minus 5 all over x plus 2 times x squared. Let us use x squared plus 1 again, quantity squared, then dx. So just like the previous one, there will be 3 partial fractions, 1 for the linear factor x plus 2 and 2 for the quadratic factor x squared plus 1, which is repeated 2. So let us break this down into partial fractions. So x squared minus 5 all over x plus 2, x squared plus 1 squared. Supposing that you have two quadratic factors in the denominator. So you have x squared plus 2 squared and x squared plus 1 squared. So how many partial fractions will there be? Quadratic factor repeated twice, quadratic factor repeated twice. So for x squared plus 2 quantity squared, there will be two partial fractions. There will be 4 constants, right? X squared plus 1 squared, there will also be two partial fractions, 2 constants for each, so another 4 constants. So all in all, just for this problem, there will be 8 constants to be determined, all in all. So it requires a lot of time and effort to calculate for the constants. But of course, there is a software available for that. Software that will break down a rational function into several partial fractions without calculating for the constants manually. So, but we have to do it the long way. So a over x plus 2 plus b times, we're now in the quadratic factor x squared plus 1, so b times 2x plus c all over x squared plus 1 plus d 2x plus c or plus e all over x squared plus 1 squared. So this will be equivalent to a times x squared plus 1 squared plus b times 2x times x plus 2 times x squared plus 1 plus c x plus 2 times x squared plus 1 plus d times 2x times x plus 2 plus e times x plus 2. Okay? So x squared minus 5 is equal to a. Expand this to x raised to 4 plus 2x squared plus 1 plus b. Well, we have here x times x squared is x cubed. So 2x to the 4th. Then 2x squared times 2x is 4x cubed. X times 2x is 2x squared. 2 times 1 is 2 times 2x is 4x. Plus c times x plus 2 times x squared plus 1 is x cubed plus 2x squared plus x plus 2. Okay. Then plus d times 2x squared plus 4x. Okay. Plus e times x plus 2. So let us compare coefficients. X to the 4th, 0, a plus 2b. X cubed, 0, 4b plus c. Okay, then x squared, that will be 1, 2a plus 2b plus 2c plus 2d. Then x, 0, 4b plus c plus 4d plus e. then the constant, negative 5, a plus 2c plus 2b. Okay. So we have 5 equations in the unknowns a, b, c, d, and e. Okay. We can replace all b's by, or all a's by negative 2b. So we can replace all a's by negative 2b. In that way, we'll be eliminating one of the unknowns a. But we can use comparing coefficient method in combination with the substitution method. Remember the substitution method, wherein we substitute a value to x to make the factor or one of the factors 0. And in here, let us say x is equal to negative 2. So all factors x plus 2 will become 0. Right? So if x is negative 2, x plus 2 will be 0. So if we go back to this portion, all terms with x plus 2 will vanish, right? So substituting negative 2 to x, will be getting negative 2 squared minus 5. That will be 4 minus 5, or negative 1, equal to a times negative 2 squared is 4 plus 1 is 5 squared is 25. So immediately we'll get the value of a equal to negative 1 over 25. Right? So if a is negative 1 over 25, we'll be able to find the value of b. And then since we have the value of b, we can calculate for c. And if we have the values of a, b, and c, we'll be able to calculate for d. And eventually we'll be able to calculate for e. So you just verify these values. A is negative 1 over 25. B will be equal to 1 over 50. C will be equal to negative 2 over 25. D will be equal to 3 over 5. And E will be equal to negative 12 over 5. Okay, so you can verify all these values. Since we already have the value of a equal to negative 1 over 25, so everything else will follow. Okay, so let's go back to our integral. It becomes a negative 1 over 25 over x plus 2 plus b is 1 over 50 times 2x over x squared plus 1 plus c is negative 2 over 25 over x squared plus 1. D is 3 over 5, 2x over x squared plus 1 squared. And E is negative 12 over 5 over x squared plus 1 quantity squared everything dx. So we integrate negative 1 over 25 ln of absolute value of x plus 2 plus 1 over 50 ln of x squared plus 1 minus 2 over 25 dx over x squared plus 1 is arctangent of x over 1 or x plus 3 pips 2x over x squared plus 1 squared. That is what we use the power formula, so it becomes x squared plus 1 to the negative 1 over negative 1 minus 12 over 5. Okay, we know the integral of dx over x squared plus 1, which is 1 over 2a cubed, or 1/2 times arctangent of u over a, so that will be x, and then plus au, from the formula we have derived in the previous example, au, so that will be x all over x squared plus 1 plus c. Okay, so let us factor 1 over 50. For the first two terms, we factor 150, so it becomes ln of x squared plus 1. 50 divided by 25 is 2, so 2 becomes the power of x plus 2, and since it is negative, it will be in the denominator, x plus 2 squared, there. So minus 2 over 25 arctangent of, okay, let us combine these two arctangent. Let us combine these two arctangent. See this? 2 over 25, negative 2 over 25. And how about this one? It becomes negative 6 over 5. Huh? So 2 over 25 and 6 over 5. Negative 2 over 25 and negative 6 over 5. So that will be negative 2 minus 30 over 25, negative 32 over 25. Negative 32 over 25. Arctangent of x. And then, oops, what happened? Okay, so negative 32 over 25 arctangent of x. Then negative 3 over 5 x squared plus 1. How about this one? This is negative. This, I can cancel this, okay? It will be 6. So negative 6 over 5 x squared plus 1. Let's see. Okay, negative 12 over 5 times 1/2 is negative 6 over 5 times x. So negative 6x over 5x squared plus 1. And so the final answer will be in the form 1 over 50 ln of x squared plus 1 all over x plus 2 squared minus 32 over 25 arctangent of x minus, okay, we can factor negative 3, that will be 1 plus 2x all over 5 x squared plus 1 plus c. So let us box our final answer there. As an exercise, you evaluate 2x squared, make it 2x cubed, minus x squared plus 2 all over x squared plus 4 squared dx. Okay?